Wonderful. There's the recording. So thank you everyone for being here today. This is our second installment of the Women in Combinatorics virtual colloquium with our distinguished speaker series that we are so happy to be putting on in collaboration with the Society of Mathematics in Mexico. We have had some great turnout last week as well as this week. Just a quick reminder that we will be hosting a coffee hour after the seminar today, or the colloquium today, where we can all have a chance to talk about our ideas and network a little bit more, and hopefully just enjoy that conference networking that we have been missing over the last few years. Especially today when we have so many speakers and guests from Mexico and who are affiliated with the SMM. So thank you again to the SMM for all of your support in organizing this, in helping us find speakers, and in spreading the word of these events. Today, I'm very much looking forward to our talk. If you have questions for the speaker, please feel free to put them in the chat and I'll be monitoring that for the duration of the talk. There's no need to keep your video on or off, whichever you prefer. And without further ado, I'm pleased to introduce Dr. Erika Roldàn, who is currently a postdoc at TUM in Munich, as well as EPFL in France. And today we will be learning about hexagonal sliding puzzles and some of their parity properties. So thank you again, Erika, for being here today, and take it away whenever you're ready.
Yeah, thank you very much for that introduction and for the invitation. I'm pleased for speaking this series with the Sociedad Matemática Mexicana and WinCom. It's not the first time that I speak at WinCom, and I think it's a great community. Yeah, so, okay, let me tell you, I'm going to tell you a story that started with a puzzle that I know for quite a long time, and I think a lot of people might be might know it and play with it. It's sliding puzzles, and probably you have played this particular sliding puzzle that is called the 15th. And before telling you what it's about, is just let me tell you when it was, like when people got the first time that people got crazy about this puzzle, and we're going to see why. So let me describe you what is the goal of the puzzle. Is you have this 4x4 square, and then you have square tiles number 1 till the 15th, and then you have one missing. So it's like the 16th tile is missing, and then the idea in this particular puzzle that you see is to be able to arrange all the numbers in order, and that is almost done. But as you can see, the 15th and the 14th are exchanged here. So these are not in order, and you should be able to, or you are requested to put them in order to solve the puzzle, and then to get the configuration that is on the right side. And then you can start trying to do it, and people start trying to do it in the USA and also in the UK and probably in other places around the world. And well, they started to feel very uncomfortable by the fact that they were not able to solve it, and there was a reason. It's because it is unsolvable. And so I'm going to tell you part of the story that is very important for what we're going to encounter later for hexagonal sliding puzzles, is that the first mathematical proof that this is unsolvable was by Johnson in 1879, and it was published in the American Journal of Mathematics. And actually the paper is called the 15th puzzle, and it's 2 parts. And this is the first part. The first part of the paper proves only that the 15th puzzle is unsolvable. And then I think some of us have heard of why it is unsolvable, but let me define it, because I think it was not seen like that, or not defined like that in particular, but it's going to be important for us, this definition. And me and my collaborator, we thought this is the exact definition that we need for talking about this property, and it's we call it the weak parity property. And basically what it says is that if you start from any configuration then it's not possible. You cannot reach any other configuration that is obtained by applying an off permutation to the label tile. So basically what you do, let me go back. So you fix the position of the holes. So here on the right and on the left, the position of the hole is fixed. And then you ask how many times or how many truss positions do I need to do of the pieces to go from one configuration to another one. So now you're not sliding the pieces. Now what you're doing is that you're picking them up and you're transposing them. And then you count how many times you need to do that in order to go from one configuration to another one. And here, for example, it's only one transposition you need to do on the pieces on the left configuration to go to the right configuration. And so what Johnson proved is that it is not possible. So this is called the weak parity property, and it's proving only unsolvability. But what it's not answering is, okay, then which puzzles are solvable? So, and one natural question, of course, is asking, are they even are those that are attained by an even permutation solvable or not? And that's the second part of this paper. And we call it the strong parity property. So the strong parity property tells you, okay, every time that you can go from one configuration to another or attain one from another by doing an even permutation of the tiles, then you will be able to attain it by sliding the tiles. So these are two different properties. The first one is like an obstruction property that is telling you cannot attain the ones that are require you an odd number of permutations, and then the other one is telling you actually you can attain all of the ones that are at even amount of permutations. And this part of the paper was written by W.E. Story, and is the same paper. Yeah, so this is the whole story of the 15 puzzle, and actually the proof works for all boards that are n by n or n by m, so rectangular boards or square boards where you have one missing tile. So this is important, is how many tiles you remove. And then you can ask me about this property of which puzzles are solvable. And actually what happens in this kind of boards is that once you have two tiles removed, then all the puzzles are solvable. So we're going to put a definition on this that is going to make it clearer. And that definition is a puzzle graph. So what we're going to do is we're going to define this puzzle, this graph on puzzles. So let me first show you, just to go directly to the sliding puzzles, the family of sliding puzzles that we want to address. And these are the hexagonal sliding puzzles. So let me give you the easiest one. Now you have three hexagons like that. And what you want to do is you want to slide the tile A in the different positions. And let's do it together here. Just want to make sure that everyone is able to look at the camera. Yeah, can everyone look at the camera? But I think
yes, it looks awesome.
Yeah, let me see something, because I think the camera is stuck. Why? Yeah, I need to restart the camera. But well, I'm gonna share it, the other thing again, and we're gonna go back there after because it's stuck. Anyways, so one of the important things to notice here in the hexagonal sliding puzzles is that you need to remove two tiles to be able to slide the tile. So if you only have one tile that is removed, you will not be able to move it. It's stuck, right? So that's the first main difference with respect to the square sliding puzzles. And by the way, I wanna make an announcement here. Up to now, and I'm almost sure this is the first time that someone has created hexagonal sliding puzzles, like physically. And I don't know what was the reason that people were not doing that. It sounds like a very natural thing. I understand why people wouldn't do it in the triangular case, because then you have orientability. You have two different orientation of the tiles, but in the hexagonal case, I think it's a very natural thing to do. Anyways, so you have three positions for the tile A once you have two tiles that are removed, and you can do any of these three movements. And then the puzzle graph is the natural thing that you will think for defining here is you put a vertex per each one of the positions of the tile, and we have three positions here. It's that like the exact positions of that tessellation, and then you connect two if you are able to move the tile from one to another one by sliding it. And of course, you need to have the two removed tiles neighboring the tile that you're moving to be able to do like this. I move it in the middle of the two tiles that are missing, and then I decide if I move it to which one of the positions that are not there. Okay, so the definition also, of course, should include how many tiles you are removing. So we're going to denote by H the number of tiles that you're removing, by B the board, any particular board. And as I said, the puzzle graph is going to have a vertex per each one of the possible placement, and then an edge if you can slide the tiles to go from one to another one. So this is going to be the main combinatorial object that we're observing. And I just want to mention very briefly that this is different from the configuration space. Configuration space is taking like a continuous movement of the tiles. And if you see here, the continuous movement of this tile will give you a Y, right? And it's gonna, and actually the formation retracts to a point. So from a topological point of view, the configuration space, not always the formation retracts to the puzzle graph. And we could discuss it if someone is interested. There is a lot of interesting things that have been studied recently, recently in configuration spaces of sliding squares, because it is related to some problems of packing disk and yeah. So, but that is another story. That is a topological story of the continuous configuration space. And here we are just putting the possible placements of the tiles. Okay, so just briefly, remembering what we have so far, because we already have all the definitions that we need, and translating to what is the weak and the strong parity property with respect to the puzzle graph is the strong parity property means that the puzzle graph has only two huge components, right? And it is given by parity, even and odd. And yeah, so once we have two holes, the whole thing gets completely connected, as we said, the puzzle graph of the square case. Okay, so now one of the things that we want to answer as well is, what about other shapes of boards? We're going to see it in the hexagonal case, but just for the square case, and I think this is something very important, is that Wilson, that actually he's at OSU, abstracted these to general graphs. So take any graph and then put label coins in each one of the vertices, and then remove one of the label coins. So you have n-1 label coins and then vertices, and then you have the same game, like the sliding puzzle game, but with sliding coins on sliding label coins on a graph. And then what he did was actually completely characterizing these graphs when they are non-separable. And here we're using our new notation. So puzzle graph, the puzzle graph of when you're playing on a graph with only one coin removed is connected. So there is, it doesn't have these two components unless it is bipartite. That is the case in the squares, in the square sliding puzzles, in which case you have the strong parity property. Again, they were not using this phrasing, but Now that we have it, we can use it, and it's shorter. That means you have only 2 components, and it is given by even or odd permutation of the tiles. And now, what something that is important is that the only graph that is not like it's outside of these of this characterization of bipartite or non-bipartite is this graph that we call W. And then here something interesting happens, and is that puzzle graph of playing this coin game in this graph has 6 components. So in any other graph, either you have 2 giant components that these are given by the parity, or everything is connected. And this graph is the only graph in this game of not having one of the label coins and then moving the label coins, is the only graph that is giving you 6 components. So yeah, and actually this completely characterizes the most general thing that we will imagine to characterize that comes from this square sliding puzzle, like this mind setting. And I'm gonna make a short stop here just to ask if someone has questions so far, or if everything is super clear and we can jump to the hexagonal case. Cool. Okay, so let's keep going. Yeah, so let's go to the hexagon sliding puzzles. And now we're gonna start like a marathon of questions that I want everyone to save like an answer for themselves. And then at the end, I'm gonna reveal what was the answer, or we're gonna all work together what was the answer. And so the first puzzle is you have the configuration on the right here, and you have the configuration on the left. And then the question is if it is actually to solve this puzzle, if it's actually possible to go from the configuration that is on the right to the configuration that is on the left by sliding the tiles. Yeah, so this is the first question to everyone. If someone has a strong feeling, they can shout it now, or just keep it for yourself. It's both work. Okay, so this is the first question that I want people to think about. And I think, okay, someone said yes, that is possible to solve. Okay, perfect. So we have one guess already in the chat. If someone wants to put it on the chat, yeah, then it's good. Okay, so now let me start defining the set of boards that we're going to be working with. And here I also have a question: which board do you think is like the analogous of the boards that we are working with when we are in the square case? Because it's like it's not easy, or it's not clear. Let me start sharing the visualizer and make it work. Yeah, can you see it now? I think you cannot see it.
I can see the camera now.
Yeah, you can see the camera now. Yeah, great. So the question for me is why it isn't working. Okay. Yeah. So one question is, what are the like the boards that we want to work that actually resemble the square ones? And you can see here there is one that is like a flower type, but that doesn't resemble the square case. And actually in the square case, the n by n is exactly the parallelogram that we have here in the hexagonal case. So let me go back to the other one before we work on that together. And so the parallelogram, we're gonna denote it by P, and then hexagonal here, parallelogram with hexagons. H is gonna denote the number of holes, and it's M1 and M2 are the 2 dimensions that we have. Okay, and so when we have M1 and M2 equal, then it's gonna be PHM. And So as I mentioned, this kind of research, like sliding tiles on a board of a certain tiling, it has been important for also trying to understand like disk moving on a certain domain. And Hannah Alpert was interesting in knowing what happened with the diameter of the puzzle graphs of this hexagonal, this particular family, the parallelogram. And then what she proved is that if you have long enough parallelograms and you remove 6 tiles, then your configuration space becomes maximally connected. So again, if you remove 2 tiles, we know that you can start like moving the pieces, but you cannot attain all, like not all puzzles are solvable in the parallelogram case. And then she proved that if you remove 6 tiles, then it is enough for everything to be solvable, the ones that are possible to be solved. But then, of course, one asks the question, the natural question, and I talked with Hannah, which is a collaborator of mine in another paper, not about this, but in another paper. And then she said, yeah, I don't know how to push these 6. I don't know if this is the right number of pieces that you need to remove to be able to solve all puzzles in this kind of boards of hexagonal puzzles. So yeah, the second question that I want everyone to think about and to bet is how many tiles you need to remove to be able to always be able to solve the puzzles in this kind of boards. Yeah, and also, what do you think it happens on smaller boards on this kind of shape? Like, what about 4x4 in this particular shape, or what about 3x3, 2x2, etc. Yeah. And then also there is another question, right? Like, what happens if you start, okay, we know if we only remove 1 tile, then no one can move. If we remove 2 tiles start moving, if you remove 3, like most likely you can solve more puzzles than with 2, etc. But then to think about what happens when one starts removing the tiles. Yeah, so let's start exploring together, and let's go to 2x2. So, okay, what are the vertices in the puzzle graph? And here I think it is important that we actually visualize and have clear what is going on with the puzzle. So you have a 2x2 parallelogram, and let me put here the graph that is important. So this is the shape of an n/2. Okay, so here the one that you see on the right. So if you draw like a graph that has 4 vertices, each one of the tiles, and then you put an edge that connects every time that you can actually move one tile to another, having 2 holes or 2 empty spaces together, you get this graph. So the graph on the right describes exactly how you can slide the tiles. I hope it is clear that when one can see the same puzzle, or all the information of the puzzle on the left is in the graph on the right. And then what happens is that one realizes that once the pieces are in a certain order, it's not possible to jump one piece. Like one piece is not going to be able to jump and go higher than the other one. If we put, like, here is the lowest 2 pieces, and then we start going like this in zigzag, like there is an order that is not going to be able to jump the pieces. And so, of course, what this is giving us is the theorem with respect to the n/2, and is that the puzzle graph has m1 times m2, in this case m1 is 2, minus the number of pieces that you remove, factorial components. So this is tons of components. So the puzzle graph of this sliding puzzle, no matter how many tiles you remove, you get this much components in the puzzle graph. And if you think about the analogous on the square case, what will happen is that like you have a single, the way to reproduce this behavior is when you have a single row, and then you have the tiles, and then you can only like move them to right or left. And so again, you cannot jump the tiles because you don't have space for them to do that move. And I think it was not expected that the 2×n was going to have this behavior. And so, but if you go and you do the same in the 2×2, what's going to happen is that you're going to have actually the strong parity property. So that will be like playing this puzzle here in only one square with this diagonal tile. And yeah, and another important thing is that you have two of the vertices of the puzzle graph that are giving you stock configurations. So unless you have the two tiles removed, sharing an edge, you will not be able to move the tiles. So that is also something important to take into account, and that is actually why we are not saying just connected on the graph, but we're using the term maximally connected, because there's going to always be configurations that are completely isolated, because you can actually not use the two tiles that are removed to move them. Okay. There is a question on the chat why the 2×2 case gives 12 vertices, and yeah, 12 vertices and 2 components, and has a strong parity property. So I'm gonna take the opportunity with that question, and let's do it perhaps all of us slowly. So. And then with that, it's going to be clearer, I think. Let me. Yeah. I'm gonna change to the Blackboard. Let me see if it works. Yeah. Yeah, I don't know if people can see my Blackboard. No?
No.
Not yet, no.
Not yet.
There we go.
Yeah.
Thank you.
Okay, so one, yeah, I'm gonna ask the person who asked to unmute and to come with me and try. We will do it together. Yeah. So let's see. So let's see. Is it clear that the 2×2 is giving this this graph? This is the first question.
Yes.
Yes. Okay. So let's start moving the pieces. As we said, we have 4 spaces to put the puzzle, but we want to be able to move the tiles. So we're gonna work with 2 pieces missing and 2 there. So let's say A and B are here. And again, to be able to move a tile, what we need to do, what we need to check is that 2 of the neighbors are empty. If 2 of the neighbors are empty, then I can decide to move that tile to any of the 2 positions, right? So let's start doing all the elements of this configuration of this puzzle graph. So again, this is a vertex on the puzzle graph. And what we want to do is to find all the elements that are connected to this one. So one possibility is moving A here and leaving B fixed. So let me erase this. And then another possibility is, sorry, my drawing perhaps is not super nice. Another possibility is leaving B there and moving A here. We're almost done. Another possibility is once, yeah, so let me, so now we can, now from here, so, and this is important, this is why connection, yeah, so from here to here, from here to here, from here, now we have B that has two neighbors that are empty from here. So B could actually decide to go to any of these two positions. Is that clear?
Yes.
Yeah, perfect. Yeah. So we can actually do it. So we let A fix here, and then we move B here, or we keep A fix here, and we move B here. So these are the 5 elements in one of the components. So this is one component. Now, what happens, and another component that is symmetric with A and B interchange. But what happens if we put A and B here? Could they move? So no one can move there, right?
Yeah.
Wait, why? Doesn't
they
each have degree 2?
Yeah, sorry. What I want to say is
the diagonals.
Yeah, exactly. Yeah, like that, right? So now both are stuck.
Right.
Yeah. So what we have here is 5 elements in this component, and there is one element here that is an isolated configuration, and then you have the same but with A and B exchange. Yeah, so these are the 12 elements of the puzzle graph.
Well, wait, I'm counting 7.
No, so here are 6, right? 5 in this component.
Oh.
And then here is another one, but what I'm saying is that if you exchange A and B,
okay,
you get the same the same amount. Why are A and B stuck? Because for being able to move them, you need to have two empty components that are neighboring each other and the piece. So the problem here is that this is an empty tile. This is an empty tile, but these two empty tiles are isolated from each other. So they don't allow you to move the pieces. The pieces get stuck. And I don't know where is my camera right now. I think I have 2 cameras. Yeah, now I can change. So yeah, let me show you here because my other camera is stuck. What is this?
May I turn off the screen share so we can see you bigger?
Yeah. Yes, please. Yeah. So basically, this is the position that is stuck. I cannot move them because the two empty spaces are isolated from each other. So the tiles are stuck. And the two isolated ones is exchanging these two, but I cannot slide it to do it. I need to take them up and then place them back. Yeah. And so it's like I don't think it's natural when one see the puzzles that these things are happening, right? It's completely unexpected. I have to admit that all the things that have happened with analyzing these puzzles, hexagon sliding puzzle, was unexpected and actually very different from the square case, which makes things actually topologically very interesting. Now we are starting to analyze what's happening with the configuration space of the sliding tiles, because yeah, very surprising things are happening. But have I answered the question, and also why A and B are stuck? Yeah, perfect.
That
okay,
was great. Thank you.
So let's go back. Yeah, great. So let's go back, and so also what was not expected is that in the 2x2, it happens to have this giant component with 5 elements isolated, that we don't take into account right now. But these 2 giant components that actually has this strong parity property that has only to do with odd and even amount of permutations that you need to do to the tiles to get to one to another one, right? But when you go to the n/2, you lose this. Suddenly, actually, you can only like move up and down, and they cannot jump each other. There is no space to jump each other. So you have this bunch of components that when you plug in, when you have the 2x2 matches, right? So yes, if we were, because what we want is families of boards to have a certain property, not only one board. And then let's go to the next question. What happens with the 3x3, right? And so now I allow 3 seconds for everyone to bet. Do you think that with 2 holes, we get 2 giant components? Like this property of having 2 giant components only being differentiated by the parity of the position of the tiles. And so because of the time, I'm gonna be a super spoiler. And the answer is no. There are a lot of non-trivial connected components. Each one of the non-trivial connected components has 80 elements. Okay. And but it has the weak parity property. And here's where we need actually, when we see the power of separating these 2 parts of the paper in the 1800s, 1880s, that was first proving the weak parity property, that is an obstruction thing, that you cannot reach the ones that are at odd permutation of the tiles. And here we have that. We cannot reach the ones that are at odd permutation of the tiles, but also an important thing is that we cannot reach all the ones that are at an even permutation. So we're not at that stage. We have a bunch of components that have the weak parity property, but you cannot have only 2 giant components. Yeah, so that's life with 2 holes. Question, 3 holes. So a lot of things could happen. So we could have that we get the strong parity property, and then suddenly we have 2 giant components. Or it could happen that we have a bunch of components, like big components, and then suddenly it's connected. Like there are different options, right? And here, each non-trivial connected component has 52,560 elements, and it does not have the strong parity property, and it's maximally connected. So in the sense that you don't get two giant components, you can actually reach everything. You get completely connected from having a bunch of components. Yeah, and what about the n by n? Yeah, is any question here?
I don't understand what you mean by maximally connected if they're various connected components.
Yeah, so that's why we use the definition of maximally connected. So maximally connected is going to be when you have all the possibilities that don't have the removed tiles isolated, because as we saw, every time that you have the removed tiles that do not share an edge, then you will not be able to move anything. So these are like the isolated configurations, but they're going to be isolated no matter how, no matter what you do in terms of moving, right? Like every time that you remove tiles, but the tiles that you're removing, they do not share an edge, then everything is stuck. You need to have at least two that share an edge. And so taking out, yeah.
But you, I mean, the sentence above says each non-trivial connecting components. You're already ignoring those isolated ones.
Yeah.
But are you saying that there's only one such non-trivial connected component?
Yes, there is only one non-trivial connected component when we say maximally connected. Yeah.
Okay. All right.
So two things. We're giving the number of the non-trivials, but the point is that yeah, it was like suspension to asking each one of the properties for the audience. But yeah, at the end, it was only one. We did that amount of elements. Yes, exactly. And then for n by n, well, I'm going to go back after that, after presenting the flower. But this is the last question that I asked. And this is, I think, the most important of the paper with respect to to what we wanted to answer with how many holes you need to take. So for n by n, my question is if it is sufficient to know the 3 by 3. Okay, so this is a question. Okay, now let me make a detour with another family of boards. So we leave the parallelograms and then let's go to the flowers. And the flowers actually gave us a lot of surprises. And this is the second flower. Like the first flower is going to be, will be one hexagon. The second flower is the one hexagon, and then all the hexagons that share one edge with this hexagon. And then I left this in a table of when I was staying with a friend in Brussels, and then I said to the colleagues that they have, can you solve this? Can you go from the configuration on the right to the configuration on the left? And then this is what I got after half an hour from the person, and the person disappears, but they left me this, that it should be impossible. And this is, of course, a mathematical statement from this person. And yes, it is impossible. With 2 holes, you cannot actually do that. And the question that we can ask is, okay, how many holes do we need to actually be able to solve all decent puzzles here? And then, yeah, somebody wants to, what about 3 holes? If I remove 3 tiles, is it possible to actually solve it? So let me tell you the whole story, because I only have not that much time. So if you have 2 holes, you have 24 components, okay? And then each component, again, the non-trivial components. I'm talking about the non-trivial components. And the component size is 60. If you remove 3 tiles, you have 6 components. And the component size is 132. And if you remove 4 holes, then suddenly you have maximally connectivity. And the size of the components is 210. So here we're jumping this strong parity property of the square case, where you get 2 giant components that is characterized by parity. So at least this flower is not giving us the same behavior. And one question will be is, okay, then perhaps there does not exist the strong parity property for hexagonal boards other than the 2 by 2 that we found, right? But then we went a little bit farther and we started analyzing the next flower, because we thought, okay, perhaps it's about that we are not big enough to actually have to actually capture if it has a strong parity property or not. And then actually the flower has the strong parity property with 2 holes. Once we start in this flower. So from this flower on, you will have the strong parity property with, and that was very nice. And so finally we got the actual board that is giving you the similar behavior as the 15 puzzle that has the strong parity property once you remove 2 tiles. So this is I wanted to present the happy story because there is a happy story here, but actually the strong parity property is there in a bigger set of boards. And I don't know if someone has noticed that the flower lacks like corners, like these corners give you like a triangle in the graph that you cannot escape from this triangle, right? Like it's like there is like a trap thing that is happening in a corner that if you start playing with these and you see that the tiles are close to the corner that are in the parallelogram, for example, you cannot make those tiles escape there with 2 holes. So that is actually what we're now aiming to prove. That is the only obstruction in the hexagonal case. But anyways, yeah, the point is that the strong parity property does hold for the flower family board. And now I want to, my camera is not working, but I want to show you another family of boards, and I think you can see it here. And this is the triangular family of boards. And then the triangular family of boards also doesn't have the strong parity property. I think people can see me in the camera, right? Yeah. Yeah. So these also doesn't have the strong parity. Okay, so let me. Yeah, I'm reading the. Is there a reason that the triangular board has corners? Yes. So again, we haven't proved that, but we believe that the only obstruction for having the strong parity property, once the boards are big enough, it's gonna be actually the corners. And it's, yeah, we hope to prove it. Now, let me go back to the question of how, if it is, if we know what happens with the 3x3, then we know what happens for bigger parallelograms. So if people can see my camera, I hope it's clear enough that I have a 3x3 parallelogram on the right, and I have a 4x4 parallelogram on the left. And then what happens is that actually everything that is going on in the 3x3, it's gonna like be like a heritage to the 4x4, because actually you can generate the 4x4 by sliding the 3x3 4 times like this, and every time that you do it, there is an overlap on the boards that you are using. And what's happening is that you will be able to do all the permutations needed here, and then go and do all the permutations that you need here, and then go and do all the permutations that you need here. And so at the end, what's going on is that once you know everything that happens in the 3x3, you can start generating bigger boards coming by the 3x3. And this is the patching theorem. And this was the most important theorem, I think, that we proved, and the more general one. And actually, it doesn't prevent you to generate things that are not in two dimensions, right? You can start generating these graphs and playing this graph in a non-geometric way. Okay, so the patching theorem turns it's let be a board of any shape that you want with hexagonal tiles. And now suppose that your board B is a union of two smaller boards, B1 and B2, such that we need to ask several things. The puzzle graph of the board B1H, here H is the number of tiles removed, has one large connected component containing all non-isolated configurations, so it's maximally connected. The puzzle graph of B2 as well is maximally connected, and then the intersection of both, and you ask that the intersection of both contain at least k plus 1 hexagons, and this k will depend, like here in the case of the parallelogram case is 2, so 2.3. The puzzle graph has one connected component containing all non-isolated configurations. So this way of allowing us to generate bigger boards with a smaller one, and then heritating the everything that you have in smaller boards is what allows you to prove this for more general boards. And yeah, so one corollary that we get is that the flower-shaped board is maximally connected, and then once you have 3 or more remove, and then the triangular board as well. So yeah, with this, I stop, I think, exactly on time. Thank you very much. Yeah.
Thank you so much. Let's go ahead and thank our speaker. I will go ahead and turn off. It's so nice to have the actual claps. I'm going to go ahead and turn off the recording so we can start our questions.